So now I'm going to talk about word problems, but maybe I'll no questions. Okay, let's talk about word problems. So we introduce word problems as a story with a question, and we talk about the idea of an answer and a solution. So this is actually the very first word problem in the curriculum. 3 little cats are in a line. How I wish they could be mine. 2 are awake and ready to leap. How many cats are still asleep? And so the picture tells the story, and we sort of sing a little question. And to solve it, 3 minus 2 equals 1. 1 little cat is still asleep. Thank you, Pablo. I was trying to figure out what there's an initial activity which is choose the picture to match the story. So we have 2 pictures, and the student has to choose the one that matches the story. So that's that's a line of activities that we have that I haven't really got into is showing a picture and multiple pictures and asking which one matches the story. So that's a way that we teach them to sort of think about a word problem or think about what situation it represents. So that's why there are 2 different pictures here, because the first step is we ask them, you know, what picture represents this story. And then once we have the picture, that's like a problem statement in pre-K and in K, actually. The quote-unquote problem statement of a word problem is always just a picture. And so 1 little cat is still asleep, so they make the equation 3 minus 2 equals 1, which we call the solution to the word problem, which is, at least in pre-K and K, always a single numerical equation. And then we say you solve the word problem. So here's another example in pre-K. We gave Dixie 4 green apples, then we gave her 3 yellow pears. How many pieces of fruit does Dixie have in total? And the students first build a concrete model and then build a representational model. There's a missing "and" in that slide. There are 2 different models here, the concrete one, the apples and the pears, and the representational one, which is the colored tokens. And then, of course, we make the abstract model.
Is there a way to repeat the question?
Yes. Yes and yes is the answer to that question. So if the student hasn't automatically answered after, how many seconds, Pablo? 20 seconds, the question will just repeat, and the student can always, well, technically, there's sometimes a separate reminder, which is different than the question. But they will always, it may not be the literal repeat of the question, but they will get a reminder every 20 seconds or something, and they can always hit that question mark to hear the reminder. So that's the question mark that you've seen all over the place. It just is a reminder of what the question is. And in questions where there are word problems, it will include reading the statement of the problem, or sometimes if it's a more complex problem, at least the part of the word problem they need to answer the given question. So that's sort of a special case for word problems. The reminders tend to be longer. Right. So first they make the concrete model, then the representational model by painting tokens, and then they make what we call the solution, which in this case would be the equation, the numerical equation, 4 plus 3 equals 7. So that was in pre-K. In K, we formalize the process for solving word problems somewhat. We follow the same series of steps, analyze the story and build a model to represent it, make a numerical expression to solve the problem, evaluate this expression to complete the solution, that is, complete that equality, and then write the answer. And so those steps are shown here, or some of this, so let's sort of go through it. 4 purple monsters and 3 orange monsters. We're riding a roller coaster. How many monsters in total are riding a roller coaster? So there's the problem statement up top in that picture, and you can see one of the ways that we develop the difficulty is how clear the picture is. In this case, the picture is already a concrete model, right, because there the monsters are in a row. And so the specific activities we give the children are, there are 4 purple monsters, paint 4 circles purple. Then there's something very interesting, and that's what is represented in the left-hand slide here. We say, do we need to add more tokens or cross some tokens out? And the student has to click on the plus sign or the minus sign. This is trying to model the thing that a teacher would do in the classroom when they're working with a student to build a token model and just say, okay, do we need more? Should we use another color? Should we take some tokens away? And so this is something that was pretty intensely debated, how exactly we should do this. Should we let them build a wrong model? And what we decided to do was just always ask, well, should we cross some tokens out or add some more tokens, and let them answer by clicking a plus or a minus sign, which seemed like an acceptable way for them to answer because they're also indicating whether we should add or subtract to solve the problem. So after the student says, or we help them to see that they should add, then we say, great, paint 3 more tokens orange. That completes the model. And then they have to show 3 plus 4 equals 7. And notice in this third screen, if they get 3 plus 4 right, but not 7, then we'll show them that number house, and you can see the relevant rows are highlighted to remind them that 3 plus 4 is 7 and ask them to just try again with the right-hand side. On the other hand, if they make a more fundamental error, then we'll have a longer discussion where we say, well, first there were 4, how many purple tokens are there? Okay, 4, drag the number 4. How many orange tokens are there? Great, drag the number 3. Do we need to add or subtract? We need to add, and then what's 4 plus 3? And then finally, folks who are familiar with our Foundations curriculum should not be surprised that we always write the answer to a word problem separately. We have a solution and an answer. And so you can see we have a unit there. That picture is a unit. So the answer is 7 monsters. And the student drags the 7 from the solution line to make the answer. Yeah?
Who did measure the student's answer? It was 4 plus 3 or 3 plus 1.
Oh, yes, for technical reasons. If they put in 3 plus 4, we'll say, you're right, but let's match the model, 4 plus 3 equals 7. And we'll switch it to 4 plus 3 equals 7. The reason we do that is a technical one. Each exercise is sort of independent and doesn't actually know what the student submitted in the previous exercise. So we don't have any way to keep the 3 plus 4 there on the screen for the next exercise. Yeah, but we don't count it as a mistake. We just say, yeah, you're right, but let's match the model. 4 plus 3 is 7, and swap the order. So yes, this is, yeah, maybe I won't say anything more about that. And it's similar behavior whenever we have, commutative, something where there's multiple correct answers. But yes, we are very careful to count mathematically correct answers as correct, even if they weren't the ones we're expecting. So problems start to include more complex calculations. There are 10 clouds in the sky, 8 of them are rain clouds. How many clouds are not rain clouds? This is also an example of a different type of word problem and a different type of model. So you'll see it's the same sequence of questions. Okay, let's paint 10 dots for the 10 clouds. Now do we need to add more dots or paint more tokens or cross them out? This time the student should answer that we cross them out. And the student can click on the tokens to cross them out. This is, by the way, another example of the same principle that was just mentioned about alternate correct answers. We allow the student to cross out any 8 tokens, but we'll sort of and count it as correct, but then we'll kind of clean it up for the future exercises so that the 8 on the right are crossed out. So kind of a similar case to putting the add-ins in the opposite order. Once we have the model, the logic is the same. We have them build an equation. And would we? I think we would show a number house for 10 to scaffold. Would there be some scaffolding if they get the calculation wrong? And then make the solution, and then I drag the answer, and you can see there's a little picture of a cloud for the unit. Students solve some new types of word problems, such as finding the difference between two quantities, finding the bigger or the smaller quantity. If you remember Roger Howe's presentation a couple of years back, probably some of you remember that, he talked about the 14 types of one-step addition and subtraction word problems that should be introduced in first grade. Let me see if I can test myself and remember all 14 types. You could have part whole with an unknown part or an unknown whole. That's 2. You could have a change to a quantity, and it could be an increase or decrease, and you could not know the initial amount, the final amount, or the change. So that's 6 types. And then, what's the other one? Oh, you could have comparison, where either it's more than or less than, and you don't know the greater quantity, the smaller quantity, or the difference. So that's 6 more types. So this is something that's quite subtle. To an adult, you might say, what do you mean? There's only 2 types. You add or you subtract. But a child doesn't know that and does not experience all of them as the same. So in this problem, Ruby flew 5 kites. Maya threw 4 more kites than Ruby did. How many kites did Maya fly? The solution is going to be 5 plus 4 equals 9. But the model is different because, let me just go back 2 screens. To a child, this problem with the monsters is not the same type as this problem where we are comparing different quantities, because it's comparison, right? We have 4 more. So the way we make models for more than and less than, as you can see here, well, first we make 5 dots for the Ruby's kites. Then we know that Maya had as many and 4 more. So first we make as many, and then we say, okay, do we need to add more or cross them out? Well, it's 4 more, so we need to make 4 more. And then the final piece is the same as other word problem types. We make 5 plus 4 equals 9. We would show a number house if they made a mistake, etc. I should say, by the way, just to give a shout out to somebody on my team, it was Emily Mataro who worked out standard scripts for all these word problem types and sort of worked closely with Vlad on the details of all of these models. So the 2 of them, Vlad and Emily, put a huge amount of effort into all of these, working out what all these sequence of steps should be for all these cases. So let's talk about first grade. Students learn to work with the text of a word problem. That is to say, read the statement, identify the givens, build a model to represent the problem, build a numerical expression, evaluate the expression, write the answer. So there are several ways that we develop this further in first grade. Probably the most obvious one is we introduce text. This is almost the only text that the student needs to read in first grade. There are a few other cases where we have like a table that says add and sum, and they need to fill it in. But almost all of the text that is there for the student to read, if they can read, is word problem text. And we do always read it. They can always hit that question mark button to hear it. So we never, a student who cannot read should still be able to solve the problems, but we know that some students can read and are there, that they should all be learning to read, and we want to support that. So you can see we start by having the givens as a picture. So what that means is even if you can't read, the relevant things should jump out at you. And the method, as you can see at the bottom of the screen, is exactly the same as what we've done in pre-K. So the only difference here is that we have text instead of just pictures and birds. We gradually transition from text where the givens are represented by pictures to a text-only problem. So here you can see the relation more than is given with the numeral 2, whereas we still have a picture of 8 planes, or however many planes that is, 9 I think, and 10. And you can see on the bottom of the screen it's the same method of solution and the same model that we used for Maya's kites. The next step in the progression with text is having a picture only for the unit. So now the picture represents a unit, and then eventually we'll go to full text. Something you should also notice on the screen is that we transition from token models to segment models in first grade, and there are a couple of reasons why we do that. So the logic is pretty much the same, but we now draw segments instead of tokens. So why do we do that? There are 2 reasons. One is I was just listing the 14 types of word problems. Some of those types are extremely difficult to do with tokens. In fact, the hardest of all of those types is a change where the original amount is unknown. Something like, there were some birds on the branch, 3 flew away, and now there were 5. How many were there to start? So if you give a child tokens and ask them to do that problem, they actually can't do it because they don't know how many tokens to put out. But if you have a segment, you can write a big segment and label with a question mark and say, okay, 3 flew away, so what has to be left? So that's one reason to introduce segments. The other reason is the numbers get big. We don't want to, past 10, it's pretty unwieldy to work with tokens. You're likely to make an error counting. So it's just a slightly more abstract model that is more convenient for some of the more difficult word problem types and also allows you to work with bigger numbers. And I should say we do have all 14 types in K, pre-K, and first grade, but some are more represented than others. Oh yeah, Pablo wants to point out that yes, these segments are always proportional. So if we say 3 and 16, the 3 is really 3/16 as long as the 16. And we changed numbers. I guess sometimes if it's 90 and 1, we didn't perfectly nail it, but we tried to be very careful with that so that we were building number sense appropriately. So here's a text-only problem, and you can see, maybe I'll just talk a little bit about the segment models here. We have 16 planes and 3, so we make a segment for 16. We show a part of it as 3, and then the unknown is represented by a question mark. We make 16 minus 3. And I should say, for every type of calculation, including the 16 minus 3 here, if the student makes a mistake on the calculation, there will be some appropriate scaffolding. There'll probably have to be a whole other talk to show you all the different types of scaffolding for different computation. Within 10, we use number houses. We also have some other visual models. I showed you the crossing 10 model. Sometimes we'll take them to a secondary screen if there isn't room to go through the calculation. So that's actually true throughout the course, that especially in first grade, that if there's a calculation which needs some more dedicated scaffolding, we will just have a secondary screen where we go through whatever the appropriate visual model is for that type of calculation. I think for the 16 minus 3, it would be a bundle of 10 sticks, and then 6 more sticks with 3 of them crossed out. But, okay, and here's a word problem about comparison, where we're using text and also using a segment. So next we begin, this is, I guess, kind of the final progression. After we've learned text and segment diagrams, we begin to solve 2-step word problems in first grade. So, and then this is going to be our last topic, by the way, other than your questions, which is how we introduce 2-step word problems. So the first thing we do is we just give 2 separate 1-step word problems. Kenji built 17 castles, Bingo knocked down 5 of them. How many sand castles were still standing? You can see we label the big segment with 17, then 5, then question mark. We make 17 minus 5. This hasn't come up before, so maybe we just point it out. How do students make 2-digit numbers? They do it by dragging 1 digit at a time. If you look carefully at the drag and drop targets, you can see that some of them have space for 2 digits. And that's always how the student makes a 2-digit number. We call them input fields internally, even though the student obviously isn't typing, but they're sort of dragging each digit. After that word problem is done, we show a second word problem. Bingo, knock down 5 more of them. How many sandcastles did Kenji have at the end? And solve that word problem. The next step in the sequence is to just have a word problem that has 2 questions. Oliver found 30 big brushes and 20 small ones. 40 of them were dirty. How many brushes did he find in total? How many brushes were not dirty? And you need to know the answer to the first question in order to solve the second question. I should say, just to point out, because this is always how the Russian curriculum works, we're trying to do a couple of different things at once. You can see, of course, we're also practicing addition with round numbers, addition and subtraction with multiples. So the next step in the progression is to insert the auxiliary question. So Ruby had 10 orange lanterns and 5 yellow lanterns. She gave 1 lantern to Maya. How many lanterns does Ruby have left? And so in order to solve that question, you need this auxiliary question. How many lanterns does Ruby have at first? So we just add that in. And then finally, a 2-step word problem. And so now I'll kind of take you through what the whole thing looks like. Penny caught 5 fish, then she caught 2 more fish, but 3 fish swam away. How many fish were left? So first, we show how many fish there were at first by dragging the number 5. Then we show how many she caught second by dragging the number 2. And now, so how many fish did she catch in total? And they should drag the question mark because we don't know how many fish she caught in total. And so this is the step of introducing the auxiliary question and realizing that the thing that we don't know that we need to find has to be marked with a question mark. Then we solve that word problem. We make the equation 5 plus 2 equals 7. And then we make a new model out of our existing model. So that question mark gets replaced with a 7. And now we make a model for the second step.
And they consider the segment stays the same from the first step.
Right. The segment stays the same. It's just, it's actually after we get the number 7 here as the number of fish that were caught in total, we replace the question mark with a 7. So now 3 fish swam away. We don't know how many were left. And now we make an equation to solve the second part, 7 minus 3 equals 4. And then we drag the answer, which is 7 fish.